Welcome to this lecture on higher order differential equations. Today, we are going to explore how mathematics captures complex, multi-layered changes in the real world. Whether you are looking at the suspension of a car or the sway of a skyscraper, understanding these equations is the key to unlocking how physical systems behave over time. Now that we know what we are studying, let us understand why these layers of change matter. Imagine you are driving a car down a highway. Your current position is your baseline. Your speed is how fast that position changes, which is the first derivative. When you step on the gas, you experience acceleration, the second derivative. And if you slam on the brakes, you feel a violent jerk, the third derivative. In mathematics, the order of a differential equation is simply the highest derivative it contains. If it has a second derivative, it is second order. These higher order equations allow us to model systems where multiple forces are acting at the exact same time. Building on that intuition, let us look at how we write these equations mathematically. This long equation is the standard way to write a linear higher order differential equation. The symbol n represents the order of the equation, like 2, 3, or 4. The variable y is the unknown function we are trying to find, while x is our independent variable, like time. The terms with a are coefficients, acting as multipliers. Finally, g of x on the right side represents any outside driving force pushing on the system. If this driving force is 0, the system is resting naturally, and we call the equation homogeneous. Before we solve our first problem, we need a strategy. How do we actually find the unknown function y? For homogeneous equations, we make a very clever guess. We assume the solution looks like an exponential function, specifically y equals e to the power of r times x. Why do we choose an exponential? Because the derivative of an exponential function is just a multiple of itself. This perfectly matches the structure of our differential equation, where a function and its derivatives are added together to equal 0. This brilliant substitution will transform our complicated calculus problem into a very simple algebra problem. Now that we have our strategy, let us see this with a concrete example. We want to solve a simple second-order equation. Y double prime minus 4y equals 0. This describes a system where acceleration is directly proportional to position. We start by guessing our solution is y equals e to the power of r times x. To substitute this into our equation, we need its second derivative. The first derivative brings down one copy of the constant r. The second derivative brings down a second copy, giving us r squared times the original exponential function. We are now ready to plug this back in. Continuing with our substitution, we place our second derivative directly into the original equation. This gives us r squared times e to the rx minus 4 times e to the rx equals 0. Notice that both pieces share that exponential term. We can factor it out to simplify the expression. Now, a fundamental rule of mathematics states that an exponential function raised to a real power will never exactly equal 0. Therefore, the part trapped inside the parentheses must be exactly 0. By dropping the exponential term, we are left with a simple polynomial called the characteristic equation. Let us finish solving this characteristic equation. We add 4 to both sides to get r squared equals 4. Taking the square root yields both a positive and a negative answer, giving us two distinct roots, positive 2 and negative 2. Because we found two different values for r, we have two separate building blocks for our final answer. We multiply each block by an unknown constant, c1 and c2, and add them together. This final equation represents all possible solutions. The positive exponent represents rapid growth, while the negative exponent represents a part of the system that shrinks and fades away over time. Having mastered the second-order case, let us step up to third-order systems. These equations involve the third derivative, which represents sudden changes in acceleration, like the jerk you feel in a car. The strategy remains exactly the same. We use our exponential guess to turn calculus into algebra. However, because it is a third-order equation, we will end up with a third-degree polynomial, which means we need to find 3 roots. Sometimes the algebra gives us the exact same root more than once. When a root repeats, we must multiply the second instance by the variable x to ensure our building blocks remain mathematically independent. Let us apply this to a slightly more complex example. We want to solve y triple prime minus y double prime equals 0. Just like before, we guess y equals e to the power of r times x. Because this is a third-order equation, we find the third derivative, which brings down the constant r 3 separate times. Substituting this back in, we get r cubed times our exponential minus r squared times our exponential equals 0. Once again, we factor out the common exponential term. Since the exponential cannot be 0, the algebraic polynomial left behind must equal 0. This leaves us with the third-degree characteristic equation. R cubed minus r squared equals 0. To find the roots, we need to factor it. Both terms share a common factor of r squared, so we pull that out to the front. This breaks the complex polynomial into 2 simpler pieces multiplied together, r squared and r minus 1. Setting the first part to 0 gives r equals 0. Because it is squared, this root happens twice. It is a repeated root. Setting the second part to 0 gives our third root, r equals 1. Now we build our final answer using these 3 roots. For the repeated root of 0, we write c1 times e to the 0x plus c2 times x times e to the 0x. Notice we multiplied by x because the root repeated. For the root of 1, we add c3 times e to the 1x. We can simplify this expression to make it much cleaner. Any number raised to the power of 0 is simply 1, so the e to the 0x terms disappear. This gives us a final simplified solution. The first 2 terms represent steady, unchanging motion, while the third term represents exponential growth. So, we have proven we can solve these equations. But why do engineers and scientists care so deeply about them? Higher-order differential equations are the fundamental language of mechanical and electrical engineering design. When you drive over a bump, your car's suspension bounces. The position of the car depends on its mass, the stiffness of the spring, and the shock absorber. Because this physical relationship involves acceleration, it absolutely requires a second-order differential equation to design a smooth, safe ride. Similarly, engineers use third and fourth order equations to ensure airplanes do not vibrate apart in the sky and tall skyscrapers do not snap during high winds. Let us visualize this with a diagram. What you're looking at is a classic mass spring damper system, the most common real-world example of a second-order differential equation. On the right, the block labeled m represents the mass, or inertia, which relates to the second derivative, acceleration. The damper labeled c represents friction or air resistance, relating to the first derivative, speed. The coiled spring labeled k represents the restoring force, relating to the actual position of the object itself. By combining these 3 physical elements, engineers create a mathematical model to predict exactly how the system will bounce and eventually settle. To wrap up our lecture, let us review the key takeaways. Higher-order differential equations are powerful tools that allow us to accurately model complex systems where rates of change themselves are constantly changing. Remember that the order of the equation is simply the highest derivative it contains. By using an exponential guess, we can transform intimidating calculus problems into straightforward algebra problems, finding characteristic roots to build our solutions. Mastering this topic unlocks the ability to understand the hidden mathematical rules governing the physical world around us, from electrical circuits to towering skyscrapers. You now have the foundation to tackle these complex systems.